Hello everyone. Our next topic is distributed transaction, and this topic you can refer from book that is Distributed Systems by Colleris. Now distributed transaction is that transaction which involves multiple servers. Or a transaction wherein its operations will be executed in more than one servers. Now what is a transaction? As we all know that transaction is nothing but a set of operations that is going to work with data. Now the transaction is of two types. One is called as centralized transaction, the other one is called as distributed transaction. In case of centralized transaction, all the objects which are going to hold the data will be present in same server. So let us say if this is the servers, this is a server, then various objects having the data will be present in same server. Now with that, the transaction, which is nothing but the set of operations, will also be executed in the same server. Now this transaction is going to access the various object for executing its operations, and all those objects are also present in the same server. So this is an example of centralized server. In case of distributed transaction, the different objects having the data will be present in different servers. Let us say this object is present in server 1 and another object is present in server 2. Now let us say the transaction T is present in some other computer system. Now this transaction T will have set of operations. Now let us say some of the operations requires first object present in first server and the remaining operations requires second object which is present in second server. Now for that, the transaction will have to access the first server as well as second server to complete the execution of all of its operations. This is an example of distributed transaction. So distributed transaction is that transaction which involves more than one server. Now in this chapter, we are going to see what is this distributed transaction, what are its various types, and how it can be implemented in the distributed system. And then we are going to see some of the properties of transaction, how it can be achieved in distributed systems. Now this we have seen, a transaction, if it is distributed, then it is going to access more than one servers. Now there are various properties of transaction that is called as acid property, out of which the important one is atomicity property, and how the atomicity property can be achieved in distributed transaction we will be discussing in this chapter. Now this distributed transaction is of two types. One is called as flat transaction, the other one is called as nested transaction. So now we are going to see in detail about this flat transaction and distributed transaction, which are the two different types of flat transaction and nested transaction, which are two different types of distributed transaction. So in case of flat transaction, all the operations will be executed which are going to access different servers, because the object having the data is present in different servers, will be executed in sequential manner, that is one after another. So the transaction will go to one server, log the object having the required data, use that object for the data, and ultimately and finally you need to unlock it. Then again it will go to another server, log the object, use the data and unlock it. So this is how flat transaction works. For example, let us say T is a transaction which is generated by client machine, and let us say it is accessing three objects, object X, object Y and object Z. Now, some of the operations will be executed in object X, some will be executed to be executed in object Y, and some is to be executed in object Z. Now, if it is a flat transaction, the transaction T will go to each object one after another, and it will be locking that object, accessing the data of that object, and then releasing the lock. Now, this is very simple to implement the flat transaction, but it is going to take a lot of time to complete the entire operations. Now, we have the various example wherein the transaction having many operations to be executed can be grouped into many groups wherein the various operations of each group could be executed in the parallel manner. So, if instead of executing all the operations one by one, if possible in the distributed system, if some of the operations could be executed in parallel manner, not one by one, then the overall time that will be required for finishing the execution of the entire transaction can be reduced. Now, this is what happens in case of nested transaction. Now, in nested transaction, a transaction will be divided into sub-transactions. Again, that sub-transaction can also be divided into many further sub-transactions down to any depth of nesting. Now, we can make each sub-transaction handle some set of operations. Now, we need to analyze the transaction and find out that how the sub-transactions is to be created. Now, ultimate objective of dividing a transaction into many sub-transactions is to execute the sub-transactions of same label in the parallel manner, so that the various operations that is present in same label can be executed simultaneously, and hence the overall time that is required for executing a transaction can be reduced. Let us say in this example we have a transaction T requested by a client, and the transaction T is divided into two sub-transactions T1 and T2. T1 is accessing object X in server X. T2 is accessing the object which is present in server Y. Now, similarly, T1 and T2, they are further divided into sub-transaction, that is T11 and T12 from T1, and from T2, two further sub-transaction is being created, that is T21 and T22. So, T1 is using the object present in server M. T12 and T21, they are accessing the object present in server N. And finally, T22 is accessing the object that is present in server P. Now, herein what we are trying to do is, we are trying to make all the transactions that is present in same label execute parallelly. For example, let us say we will be executing T1 and T2 parallelly or simultaneously. That is, the object of server X and object of server Y will be accessed parallelly or at the same time. Similarly, the transaction T11, T12, T21 and T22 will be executed parallelly. That means at the same time, object of server M, N and P by transactions T11, T12, T21 and T22 will be accessed simultaneously or at the same time. Now, this way, the overall time, as I have been saying again and again, that the overall time that will be required to finish the execution of a transaction will be very less. Now, let us see an example how nested transaction works. Let us say a client has generated a transaction wherein it is accessing four objects A, B, C and D. From object A, the transaction is taking out or withdrawing rupees 10, which it is depositing in object C. And similarly, from object B, the client transaction is withdrawing rupees 20 and the same amount it is depositing in object D. Now there are 4 operations that is being performed by this transaction. One is withdraw 10 from object A, deposit that rupees 10 in object C. Similarly, withdraw rupees 20 from object B and deposit that rupees 20 in object D. So herein we are executing four operations, that is A dot withdraw means from object A withdraw 10, B dot withdraw, C dot deposit and D dot deposit. So these are the 4 operations that this transaction is supposed to execute. Now what we are doing here is, for each operation we are creating a sub transactions. So whenever we open a transaction, this is the structure for Java programming language. So whenever we open a transaction, distributed transaction, we need to use a Java function called open transaction, and when the transaction gets complete, all the operations is executed, then we need to execute a function called close transaction. Now between open transaction and close transaction, we will have set of operations that we want to be performed in that transaction. Now T, after this client, after opening a transaction, for each of the operations, so there are 4 operations, for each of the operation we are creating a sub transaction. So sub transaction in Java will be created by using open sub transaction function. So using first open sub transaction, we are accessing object A and withdrawing rupees 10. Now from second sub transaction, we are withdrawing 20 from B. From third sub transaction, we are depositing 10 in C, and from fourth sub transaction, we will be executing the operation of depositing 20 in D. So from transaction T, we created 4 sub transactions, that is T1, T2, T3 and T4. Now out of this 4 sub transaction, we need to find out which all sub transaction can be executed parallelly. So from here we can see that there are transaction T1, which is withdrawing rupees 10 from A, and transaction T2, which is withdrawing rupees 20 from B. So these are the 2 operations which is withdrawing 2 different amount from 2 different objects. Now it is only a withdraw operation from 2 different objects, so it can be executed simultaneously or parallelly. Now similarly, if we see, after withdrawing, the respective amount is getting deposited in object C and object D. So these are the 2 deposit operations to be executed in 2 different objects. So these 2 can also be executed parallelly. So what we can see here is transaction T1 and T2 can be executed parallelly, and transaction T3 and T4 can be executed parallelly. So if it was only flat transaction, then there would not be any function that is open sub transaction. So all the operation would have been executed one by one in sequential manner. Now if it is, since it is a nested transaction, we are using this open sub transaction function, and we are identifying which all sub transaction can be executed parallelly. So here in this case, T1 and T2 will be executed parallelly, and T3 and T4 will be executed parallelly, and finally the ultimate objective is to reduce the overall time that is required for finishing the execution of entire transactions. Now next we are going to see that a transaction must satisfy, in case of distributed system also, it must satisfy ACID property, that is atomicity, consistency, isolation and durability. Now herein we are going to see how the atomicity property in distributed transaction can be satisfied. Now atomicity property means when the transaction comes to an end, either all the operation of the transaction has to be executed successfully or none of the operation. Like for example, if we see this one, there are 4 operations that this transaction is performing. So atomicity property requires either all 4 operation is executed successfully, that means from A and B rupees 10 and 20 is withdrawn and that is deposited to account C and D respectively. So either all 4 operations is executed successfully or none of the operation has to be executed. So this is what is atomicity property requires. Now how this is achieved in distributed system is there are various algorithm for achieving atomicity, but the different algorithm that we are going to see in this lecture hour is they are going to require a separate server for maintaining the atomicity property, for satisfying the atomicity property, and that is a coordinator process. So herein in our distributed system we will have a process, okay, that is going to act coordinator for ensuring the atomicity property of all the distributed transactions. So what this coordinator does is when the client starts the transaction, it will be sending open transaction request to the coordinator. So that means coordinator will know that a client has started a transaction. Now when that transaction gets over, at the end the coordinator's job is to ensure that either all the operations in that transaction which was requested by the client was carried out successfully in the distributed system or none of the operation is executed. So this is how the atomicity will be satisfied by the coordinator. Now the various steps that is involved here is when the client will be starting the transaction, as I said, it will be sending open transaction request to the coordinator. Coordinator for each client, because in the distributed system simultaneously there will be many clients who will be initiating the transaction. Now the coordinator will also have to record the various transactions that has started so that when the transaction gets over, the coordinator can relate about which all object was accessed by the transaction and can make sure that the operations in all the objects, whether it is completely executed or none of the operations is executed. So when the client will be starting a transaction, it will be sending open transaction request to the coordinator. Now each transaction needs to be uniquely identified by the coordinator in the distributed system. So for that, for each transaction request that the coordinator gets from the client, it will be generating a unique identifier for the transaction that is called transaction identifier. Now usually how coordinator generates a unique identifier for each transaction is by combining two fields. One is the IP address of the coordinator and one is a unique number that the coordinator will be generating. So every time coordinator receives a new transaction request from the client, it will be generating the transaction identifier, and that transaction identifier will be sent to the client. Now what client will do is, for executing each operation, when it will be sending the request for executing the operation to that server wherein the object required by that operation is present, it will also be sending the transaction identifier to that server, so that ultimately coordinator can record regarding which all operations of that client was executed in which all server, so that at the end coordinator can request those server to send the coordinator regarding the status information whether the operations was successful or not. Okay, so the steps are: first, for the open transaction, coordinator will be sending the transaction identifier to the client, and client can have many operations, so coordinator need not know what all operations client executed. Okay, that is beyond the requirement from the distributed transaction. Coordinator only need to know that which all server was accessed for completing the execution of client's transaction. So for that, when the client will be accessing any server for the data, it will be sending the transaction identifier, and that server which is having the data will be informing coordinator about this. So at the end, coordinator will know all the server which was accessed by client transaction during the entire process. So the steps can be seen over here. So let us say here the client is initiating a transaction using open transaction function, and at the end it will be sending close transaction request to the coordinator. So when client will be sending open transaction request to the coordinator, in response to this, coordinator will be sending a unique transaction identifier to the client, that is TID. Now client will be sending for every operation, as I said, client will also be sending the TID to that respective server. For example, let us see here, client is accessing object B to withdraw, let us say, amount 3 from that server. With that operation request, client is also sending something called as T or TID. So this is nothing but the transaction identifier, a unique number that is going to identify that transaction uniquely in this distributed environment. Now herein, the various server which is having the object which this client transaction is going to access, they are going to generate a participant object, another object called as participant object, and every time a client transaction use the object of that server, its participant object will be joining coordinator for that particular transaction ID. So that means, for example, let us say when client will be executing a dot withdraw, it will be sending that request to the server X. Server X will have a participant object, and based on the transaction ID that will be received in the operation request from the client, it will be sending a join request to the coordinator. So when join request is received by the coordinator, coordinator will understand that for this particular transaction, client used the object present in server X. Similarly, when client will be sending another transaction request, let us say B dot withdraw, okay, to the server Y, because server Y is maintaining this object B, the participant object of that server Y will be sending join request to the coordinator, and in that join request it will be sending the information about TID, transaction identifier. So from here the coordinator will understand that previously transaction T had accessed the object of server X. Now transaction T is accessing the object of server Y. Similarly, for every operation, wherever the object is present, its participant object of that server will be joining the coordinator. So this is how coordinator will not know the operations that the client is performing, but coordinator will know every server that the client transaction is accessing. So this is the syntax for the join request. The first parameter trans is nothing but TID, transaction ID, and the second parameter is reference to the participant, the address of the participant object, so that at the end when the client will be sending close transaction request to coordinator, close transaction can have two value in it. One is commit, usually it will be commit only. The other one is abort. So in the close transaction, if it is commit, that means coordinator will understand that all the operations has to be committed by all the object. If it is abort, then none of the operation has to be executed. So in the join request that the participant will be sending to the coordinator, the first will be the transaction ID, which has requested for the object of that particular server, and second is the address of participant, so that at the end when coordinator gets the close transaction request from the client, coordinator will know about which all participants to be communicated. Okay, communicated the information about whether to commit or to abort the transaction finally. Now this is the overall scenario. Now to achieve the atomicity property, there are two algorithms that we will be discussing in today's class. One is called as one-phase atomic commit protocol. The second one is called as two-phase atomic commit protocol. Now, if it is a one-phase atomic commit protocol, when the client will be sending closed transaction request to the coordinator, that is the last step, based on whatever information is present in closed transaction request, that is commit or abort, coordinator will be sending that information to all the participants. Now, if the request is to abort, then there is no problem. That is, coordinator will tell all the participants to abort whatever operation request client had requested for. So, all the participating object will be aborting all the operations. Now, but suppose if the client is requesting for commit, and in that case there can be two situations. Now, if the participants are ready to commit their part of operations, then there is no problem. Let us say here there are 3 servers involved and the operations in all 3 servers can be committed, and it is also getting the commit request from coordinator, then there is no problem. All server will be committing their part of operations. But let us see if due to some reason some server cannot commit their operations. Okay, there can be so many possible reasons for that. In that case, if coordinator sends the commit request to all the participants without asking whether they are ready to commit or not, what will happen is some participants which are not able to commit, they will not be committing. So atomicity property will be violated here. So wherein some are committing and some are not committing. Now this is the problem that is there in one phase atomic commit protocol. So here in case of one phase atomic commit protocol, if it is abort, then all will be aborting. There is no problem. If it is commit, and if all the participants are in the ready mode to commit, then also there is no problem. But if it is commit from the coordinator, that is going to all the participants, but some are not able to commit due to some reason, then at that point in time the atomicity property will be violated. So that is why we have another protocol called two-phase atomic commit protocol. So as we have seen that in case of one-phase atomic commit protocol, it does not allow any of the participant to take unilateral decision on their side. That means participant from their side, they cannot decide if they want to abort the transaction. It is only from the client side. If client is saying commit, then everybody is forced to commit, and if client is saying abort, then everybody is forced to abort the transaction. In that case, we have seen previously that the atomicity property may be violated. So another revision of one-phase atomic commit protocol is two-phase atomic commit protocol, wherein it gives the bilateral decision to be taken from the client side as well as from the server side, which is maintaining the objects. So herein, in case of two-phase atomic commit protocol, what happens is that when the client will be sending the closed transaction request to the server, so when client will be sending closed transaction request to the server, now again similar to that of one phase, it will have two meaning. One is to commit, the second one is to abort. Now if the request to the coordinator is to abort, then similar to that of one phase atomic commit protocol, coordinator will be sending abort request to all the participant, and every participant will be aborting their part of transaction. Now if the request is commit request from client to the coordinator, then coordinator, instead of sending commit direction to all the participants, the coordinator will be asking all the participants whether they can commit their part of transaction or not. Now that is nothing but it will perform something called as voting. A voting phase will start. So that is coordinator will ask all the participants to vote. Vote can be either yes or no. So if the participant is ready to commit, okay, they can execute their operations permanently in the object, then they will be sending vote as yes. Now if any of the participant cannot commit due to some reason, then they will be sending vote as no. Now if any of the vote that the coordinator will be receiving is no, that means the coordinator will take a decision to abort the transaction and it will be sending abort request to all the participants. Now if all the participants send the vote as yes, it means all the participants they are in the ready mode of committing their part of transaction. So coordinator will take the decision of committing the transaction and it will send commit request to all the participant. Now participant, once it gets the commit request, it will be committing their part of transaction. So this is how the two-phase atomic commit protocol works. So why this is called two-phase atomic commit protocol is the entire phases has been divided into two parts. In the first part, once the coordinator gets the closed transaction request, it will perform the voting operation. That is, it will ask all the participants to vote either yes or no. Now, based on the vote collected, in the second phase, the coordinator will take the decision regarding whether the transaction is to be committed or aborted. That means in another way, we can say that all the participants, they are making a joint decision. They are sending their vote yes or they are sending their vote no. That means they are making a decision regarding whether the transaction needs to be committed or not. Now based on the decision that that coordinator will be collecting based on the vote, coordinator will be sending either commit request or the abort request to all the participants. Now these are the set of functions that will be executed in two-phase atomic commit protocol operations. Now the first one is when the coordinator gets closed transaction request from the client, it will be executing a function called can commit in Java, and that function will have a parameter that is transaction ID. So it will be sending this can commit request to all the participant with the transaction ID. So it is asking all the participant to give their vote. Vote can be either yes or no. So if the participant can commit, reply will be yes. If the participant cannot commit, reply will be no. So the first operation is can commit, which will be from coordinator to all the participants. Now based on the vote, in the second phase, the coordinator will be sending or will be executing operation or the function that is do commit or do abort. Now again it will have the parameter that is transaction ID. So it will be sending do commit or do abort request to all the participants. So that will be done by using these functions. Now participant, after getting the commit or the abort request from the coordinator, they will be performing the operations and then they will be sending this status information to the coordinator. Now that they will be doing by using have committed function. Now this function will be executed by participant, okay, and its direction will be from participant to the coordinator. So that means for that particular transaction ID, whether that participant have committed or not, okay. So this is the confirmation that will be sent from participant to the coordinator. Now sometimes what may happen is after participant have sent the or executed the operation that is have committed, okay, it may not get the final decision from the coordinator, okay, that whether the transaction was successful or not. So in that case, the participant can get the decision, or participant can ask coordinator for the decision that what is to be done. Is it okay? So I repeat here, get decision is executed whenever, so not after have committed. Get decision will be executed when the participant has voted for yes, that is the participant is ready to commit its part of transaction, but the participant hasn't got any of this operation request, that is either do commit or do abort operation request from the coordinator. In that case, the participant can execute this get transaction request, wherein it will be asking coordinator to give the final decision. Is it okay? Based on the vote, that is yes vote, which participant has casted, participant need to know that what it should go for, that is whether it should commit the transaction or it should abort its part of transactions. So this has been discussed in more detail here, that is in phase 1, coordinator will be executing can commit request to all the participant, and it will be collecting yes or no vote from all the participant, that is phase 1. In phase 2, coordinator will be deciding on the final decision, and it will be sending either do commit request otherwise or do abort request to all the participants, and in return to that, participant will be sending have committed as a confirmation to the coordinator. So the same thing has been shown over here. Coordinator, after getting the closed transaction request, it means it is prepared to commit, so it will be sending can commit request to all the participants, and up till now the coordinator is waiting for votes to be received from all the participants. Now participant, after receiving can commit request from the coordinator, if they can commit, then they will be preparing itself for committing the transaction. Remember that the participant object, before sending vote yes to the coordinator, it will be changing its state to another state called prepared state. So when the participant has changed for its state to prepared state for any transaction, that means all the data that the operation has executed, it will be saving that data permanently into the secondary storage, not in the object till now, because it has not got any do commit request from the server yet, but all the operations, all the changes that was performed in the data will be permanently saved. So that what happens is that after sending yes, if the server fails, okay, if the server within the object fails, then only later on, when that server will be booted, okay, or when that server will start again, still the data which it was supposed to commit permanently in the secondary storage will be present there itself. Okay, so what we have is the object is a place wherein the actual data will be present, and until client is executing the operations, those change will be present only in the primary memory or temporary memory. But when the participant will be sending vote yes to the coordinator, it means after sending yes, okay, and before actually committing all the transaction, in between, if any kind of failure occurs, data should not be lost. So that is why the participant will store or save all the updated data in the secondary storage. Okay, now when if any kind of failure occurs, still the data will be present in the secondary storage. Now when the data will be saved in the secondary storage, for that transaction ID, the participant object will be called as prepared state. So the participant will have to change its state to the prepared state, okay, that is it is prepared to commit, then it will be sending vote yes to the coordinator. Coordinator, after receiving vote yes, it means now the transaction will be committed. So it will be sending do commit to all the participant, and they will be committing. That means whatever changes was there, that will be permanently updated in the object which is maintaining the actual data. And finally, the participant will be sending have committed to the coordinator. So this was about how two-phase atomic commit protocol works. Now we will see the failure model of two-phase atomic commit protocol. So in case of two-phase atomic commit protocol, okay, we are going to see what will be the overhead here. Okay, that is how many messages is required in two-phase atomic commit protocol for each transaction. So the number of messages that will be required in two-phase atomic commit protocol for each transaction will be: one is can commit, that is one message which will go from coordinator to participant. Second one is vote, which can be yes or no. Third one is do commit or do abort. Now the last one, that is have committed message, it is optional. You may have or you may not have. Okay, so it depends on whether you as a administrator of the distributed system want to implement it or not. But the mandatory messages that must be communicated to achieve this atomicity using two-phase atomic commit protocol are can commit, yes, and do commit or do abort. So for each transaction, the number of messages that will be required is 3. Okay, so 3 number of messages will be required for each transaction completion. Now this was about how atomicity can be achieved. Now we will briefly see how concurrency can be, that is the second property of acid, okay, concurrency control, how it can be achieved in distributed system. So concurrency means similar to that of centralized system. In distributed system also, simultaneously there can be more than one transaction accessing the object. Okay, but the different transaction that is getting executed simultaneously should not be interfering with each other. That is, when the various transaction, more than one transaction gets executed in the same object, the integrity of the object should not be affected. That means if one is writing, the other one is reading, they should be arranged in such a way that the integrity, okay, or the importance or the value of the data in each object should never be affected. So this is what is concurrency control says. So there are various ways of achieving concurrency control in similar to that of centralized system in distributed system also, but the most popular one is locking. In case of locking, what happens is that a transaction before using a object will have to lock it, and after using it will have to release the lock, that is unlock it. Now when an object is locked by any of the transaction, no other transaction will be allowed to lock that object again. So that is by using locking and unlocking. Now if we use this traditional locking and unlocking, sometimes because of the process of locking and unlocking, the overall time that will be taken by all the transactions to complete their execution can be very high. And another problem is there can be a deadlock situation. That is, a transaction has locked object 1 and it is requesting for object 2, which has been already locked by another transaction which is requesting for object which first transaction is holding. So deadlock situation can occur and it may be very slow for that may not be sufficient enough to satisfy the requirement of distributed system. For the if we see the traditional locking mechanism. So for the locking also there are various variations. Okay. So One type of locking which is very much popular and that deals with the problem of deadlock is 2PL, that is two phase locking, wherein in the initially the transaction will have to lock all the object that it wants. Okay, that is called growing phase. And after using or after executing all the operation, at the end it will have to unlock all the object, that is called shrinking phase. Now if we follow 2PL, then there will not be any problem for deadlock solution. Now this shows the basic concept of how the locking works. A serialization similar to that of centralized system has been used. Now another way of controlling concurrency in distributed system is OCC, optimistic control concurrency control, wherein all the transactions are allowed to proceed as it is, because what happens in case of two phase locking is it is very much restrictive. Though it solves the problem of deadlock, but then initially acquiring all the object, locking all the object, and at the end only unlocking all the object, that makes the overall operation very much inefficient. Okay, in case of optimistic concurrency control, all the transactions are allowed to proceed. Okay, they are allowed to make they are allowed to access all the object. Okay, make changes in the data of the object, but they will be making changes only in the temporary storage. They will create a copy of that object in a temporary memory. Therein the transactions operations will be executed. Now at the end, before a transaction commits, okay, the validation of the operations of the transaction will be done. So during validation, it will be checked whether committing that transaction is going to affect the integrity of the data or not. So if the transaction can be committed, the transaction will be allowed to proceed further. Otherwise, rollbacking of the transaction will be done. So that is in case of optimistic concurrency control. So this is all about the distributed transaction. Thank you all.